Live? Oh, there it is, yep. All right, good morning. Good morning. We're dwindling a little bit in numbers for the beginning of class, but this is the strong ones here, strong students. Okay, so this is where we left off last time. We were talking about calculating texture functions, and then we've gone into grain boundaries and grain boundary texture, and the calculations of those are very similar, and I'll just briefly remind us what the harmonic functions do. But where we left off last time was this list of boundary distribution parameterizations. And so if you look at a grain boundary, if you look at the full description, which we talked about before, right here, this last one, it could include 8 parameters. We have a reference frame, an external reference frame. We have an orientation from one of the grains that bounds the boundary and another grain on the other side of the boundary. And then we have to have the orientation of the grain boundary plane, which is known in, which takes another 2 parameters. So 3 parameters for each of the distributions, for each of the orientations, 3 each, and then 2 for that one. So we have 3 and 2 and 3, so that's the 8 parameter distribution that we get. But that is inconvenient a lot of times to think in spaces that are so complex. And so what we do is we try and reduce the function to the minimum number of parameters that will help us describe the problem. So as you're going through your research, you say, do I need an external reference frame? And if you don't, you automatically can throw away 3 parameters and just work with a misorientation. So then you have functions like these, where you have a misorientation distribution function, that's the MDF, with the interface normal, that's 2 parameters, described in the reference frame or described in the crystal frame, and then you have your misorientation between the 2. So then you have 3 parameters here, 2 parameters here, which gives you 5 parameters. Now some things are good enough with just your misorientation angle, right? If you use a Reed-Shockley type of model, where we say low angle boundaries are low energy, high angle boundaries are high energy, all you need to know is that angle and you don't need to know anything else. So if you're doing a function like that, then you just use this. It's 1 parameter, works really nice. The full misorientation distribution is 3 parameters, right? So there's a number of things that you can do that will help you describe what the grain boundary is. All right, so let's remind ourselves about spherical harmonics, because these spaces are all orientation spaces or rotation spaces. And so if we have a triplet of Euler angles, which G we define, right? G is, with Bunge notation, it's phi1 and capital Phi and phi2, right? So we have those 3 parameters. We can use those in our spherical harmonics. That's these T functions. That's the full body harmonics. And then we can expand that in a Fourier series expansion to give us the distribution that we want. As we start to smooth the function, that's where we start to determine truncation order or the Gaussian half-width for the individual orientation measurements that affects this value K when we are calculating the coefficients of the Fourier series expansion. Now if we have a 2-dimensional function, so we're describing it on the surface of the unit sphere, but we don't care what the rotation angle is, we just have a polar and an azimuthal angle. So that's the space of the grain boundary plane, right? We just want to know the normal, we don't have a magnitude associated with the normal. Then we use this surface spherical harmonic, which I'm calling Y. PQ are indices, D are the coefficients for that function. And it's defined over N, or over the polar and azimuthal angles that define that unit vector. And we define that function, and that's just a function over the space of N. So if we combine those, it's very simple. We just increase the number of indices on our coefficients, and we add another function. So if I want to make this function f of g, if I want to make it f of delta g and n, right? Cross that one off. And that's going to be equal to all of these, but then we're going to add a P and Q under my coefficient. I don't know if you can read that. Maybe I should rewrite it. Add a P and Q onto that, and then I'll add a Y, P, Q, N onto this. And then we have two more summations here. No more space. Two more summations. So it starts to get L, M, N, P, Q. So it starts to get a little messy, right? And then we'll call these, we have to come up with a number on them or a letter. Let's call them just A. L, M, N, P, Q, and then you have T, L, M, N, G, of course. And then you have Y, P, Q, of N. Right, so that's the entire thing. So you can expand that. Now what if I'm, you know, we talked about having a vector if we're doing a coherence function. Now if you know what Fourier series are and how to do Fourier series generally, typically we do it with an exponential function, right? So an exponential function, so it's, we can define any space. So if we want to define a vector or a distance, we can add those into this same type of representation. So a lot of times if we're trying to define really complex functions mathematically, we can just define them using a Fourier series expansion. And we know that defining, once we have the measure of an individual measurement, an individual boundary or an individual orientation, we just plug those values in directly and we calculate the coefficients just directly as an algebraic average of everything that we have. Okay, so it can be done as complex as we want. So having these 8-dimension functions shouldn't scare you. You just know it's more summation signs. And you plug them into the same thing we've done before. Now what if we get really scary? Now we're going to talk about triple junctions, right? And I mentioned that's what we're going to collaborate on together. IIT, KGP, along with WSU, we're going to collaborate on looking at triple junctions. And so if we look at a triple junction, we have 3 orientations associated with that one triple line, right? That's where 3 grain boundaries come into coincidence with each other along a line. So we have those 3 orientations, which I'm showing here. And then we have the dihedral angles for each of those, which I'm calling alpha, beta, gamma. So here's your 3 dihedral angles, alpha, beta, gamma, GA, GB, GC. N is the direction now of, well, this is a test plane is what that is, but T is the direction of the triple line orientation. So the way the triple line is pointing is T, so that's a unit vector that's in a polar and azimuthal angle space again. So the function gets really messy, right? What we want is line length per unit volume, that's L sub V, because a triple line is a line length, right? So line length per unit volume, and we can put whatever modifiers in that function we want, whatever functional dependence we want for that triple line. So if we just want to know how many triple lines are pointing in what direction, we would just save T, and we would leave the rest of these out, right? We wouldn't include our crystallographic parameters, okay? And then the stereology equation is very similar to one that we used for grain boundaries that we saw previously, where we have a T dot N in the integral, where N now is the normal to the test plane. Sorry about reusing the value N, but now that's the test plane normal orientation. So we have a 3-dimensional structure. We cut through it with a plane, right? You measure it, you polish it up, and you look. You count up all your triple lines. That will be a points per unit area measure. That's what you're actually measuring, points per unit area. The function you want is L sub V. You go through a very similar mathematics that we talked about with Hilliard, and you get directly out the coefficients of the Fourier series expansion that represent L sub V. So we know how to solve this equation thanks to some smart people who published papers back in the 60s, right? So we can solve that equation. It's quite a simple solution. But the point is, now if we use all the functional dependence of a triple line, we want to include all that. There's 14 parameters if we have an external reference frame, or 11 if we use misorientations to describe it. Because if we're using misorientations, we can go from A to B, give us that misorientation, B to C, give us that misorientation. And then we know C to A has to take us back to the original place. So we can just set the three of those equal to an identity, and we know that we have the third misorientation. So then we can knock out three of our parameters here, and so we end up with 11. So that's what we say. There's 11 parameters to uniquely describe a triple line. The GA, GB, GC is the crystallite orientation of the grain that we measure with EBSD or something, yes. Right.
And we can include the boundary misorientation also.
Yes. Yes. Because remember the misorientation, if we want the misorientation between A and B, that's just GA times GB transpose, right? So once we know these orientations, we calculate all the misorientations. All right, so just a note that Bunga emphasized when we started first thinking about grain boundaries and studying grain boundaries. You know, it's sometimes the statisticians call it the curse of dimensionality, right? So as we include higher dimensions in our functions, then we need a lot more data points to be able to actually have any kind of statistical reliability. And this he derived very simply from something that was done back in the 50s in some mathematics. I'm not going to drive it, I'm just showing this. So if we have a function that has 3 dimensions, like our ODF, for example, right? ODF is 3 dimensions. That means we need at least 3. If that's 3, this is 3 for low resolution. So this is the log of the number of data. So that means we need 1,000 data points, right? For minimum statistical reliability on a function defined over G. Now, if we want better statistical reliability, it's going to be 1,000,000, right? So if we have a grain boundary defined in 5 dimensions, now we need 10 to the 5th data points, right? 100,000. And if we want better statistical reliability, we need 10 to the 10th data points. Okay? So statistical reliability is a real consideration when we start increasing the dimensionality of our function. So anything we can decrease down to lower dimension or combine dimensions in certain cases, then that's tricks we should be looking to play. Okay. So now I'm going to talk just about this misorientation distribution function, delta G. And it's defined by an axis defined by alpha beta and an angle omega. But if we throw out our alpha and beta, we get this kind of a plot. This is our misorientation angle histogram. And we can see what orientation angles we have to rotate one neighboring lattice into its neighbor. Right? So the orientation of one lattice rotated in a coincidence with its neighbor on the other side of the grain boundary. This is the angle that's required to do that, and this is the distribution. So this is a one-dimensional function just showing a histogram of angles. Right? You don't know anything about the axis. You don't know anything about how boundaries are connected with each other. All you know is the angle and what the probability density is for taking any random boundary and saying what's the angle of misorientation for that boundary. Okay, you get this distribution. Okay, if we include the alpha beta, then we have to plot it up in 3 dimensions. So now the angle, each one of these bins, is now being plotted as a unit triangle. Right, so this 60-degree bin is this one right here. So now you can see that all of these boundaries, or the majority of the 60-degree boundaries, have a 111 rotation axis. Okay, that's something we didn't know from this. Maybe we knew because we knew maybe we had FCC material that was heavily twinned or something. But maybe we didn't know that. So this will tell us in the distribution, you know, you can take any of these bins. So this one looks like we have a peak here between 37 and 39 something. We have this peak, and so if we go to that bin, we'll be somewhere around in here, either 35 to 40, something like that. And you can see we have a lot of 110 misorientations at that point. And it turns out that 39 degrees about 110 is the sigma 9 boundary, which is a second order twin. Right? So if you have a twin and then it twins again, you'll get a sigma 9 boundary. And so that also is consistent with what we might expect in the distribution. Well, you can measure that. It comes out directly in the functions. Okay. Now I'm going to go through a couple of case studies, just show some experimental data and what we do here. So this is a old example. Interconnects in computer chips don't look like this anymore, right? They used to look like this back in the 90s when we used a lot of aluminum instead of copper like we're using now. But there's a really nice example because the electromigration, or how much diffusion you get along these lines, is a very strong function of orientation and boundary character. So if we look at this, this is just you don't need to know this, but this is mean time to failure for those lines. How much diffusion happens is a function of how much 111 orientations we have, and we divide that either by the random or the 200 distribution in the structure. So this is specifically for looking at texture, what we have. There's also some grain size and some standard deviation of the grain size in here. We're not going to focus on these things. Okay, so here's an orientation map. This is aluminum film. This one has a high mean time to failure. If I make a computer chip out of it and run a current through it, then it will take a long time before your computer breaks and you have to go buy a new CPU or something. The distribution we're looking at has a very tight 111. So in the pole figure here, you have a very high fraction of 111 orientations. This one, as you can see right here, if you can read that, it says 127 times random with the way we calculated that. So remember, the way we calculate it is either binning or through the generalized spherical harmonic expansion. So we come up exactly, we say, okay, we have 127. If this was a completely random structure or uniform structure, this value would be 1 for how many blue grains we have, how many 111s are pointing straight up. We have 127 times random. Okay. Yeah, we won't talk about Rotkin curve. If we have a lower mean time to failure, we have this more random texture. This one is only 13 point something times random. Right? Still a lot of 111s, but there's a lot of other things. So that's a lower mean time to failure. If we look at the misorientation angle histogram, then we see on the high mean time to failure film, we have a very high distribution of low angle boundaries. And in the lower time to failure film, we have a lot more of these higher angle boundaries in the distribution. Now, if we're describing what actually happens during electromigration in aluminum, where we have polycrystalline lines, it's diffusion along grain boundaries, right? So that's what's giving rise to early failures. We get diffusion along grain boundaries. And if you have these high angle boundaries that are being shown up here, you have those high angle boundaries, it's going to be higher diffusion. Right? The diffusivity will be higher in general. Now it's a stress-directed diffusivity. You have a electrical current, right, 10 to the 6th amps or something per centimeter squared going through that line. But it's stress-directed. But anyway, these will diffuse faster, so you'll have faster failure. It's a lot easier to describe it that way than trying to say, well, I wonder if 111, the low surface energy, has lower diffusion, lower diffusivity because it's a low energy surface than a 200 surface, for example. And so maybe it's surface diffusivity that causes that issue. But in this case, it's all the boundaries. And so it's not really the texture from that equation that we showed that's governing the behavior. It's actually the grain boundary character that governs that behavior. And we don't need to go in and look at an axis of rotation and all those things. We could and come up with the same information. But all we need is this misorientation angle plot, right? So we're talking about grain boundaries. We do a one-dimensional parameterization. We come up with a really nice conclusion of what's going on in our structure. I should have put this first about what happens, but this is how you measure the misorientation or the time to failure. Now there's another parameter that's important, and we don't get this in looking at our misorientation angle histogram, and we don't get it at looking at the misorientation distribution function. And we don't even get it in looking at the function that has the misorientation and the boundary plane. 5 dimensions, 8 dimensions of data, we still don't get any type of information on how things are connected. So if we're really interested in that, then we go back to percolation theory or topology. Sanisha was mentioning topology last week a little bit. And you have topological parameters that can be defined for boundaries that will describe how those are connected. Percolation will say if you're looking at a specific type of boundary, let's say we want to see if our high angle boundaries are all connected with each other. So let's say the red would be high diffusivity paths. So the grains, the atoms would be diffusing rapidly along there, and now all of a sudden we have 2 points where they're low diffusivity, right? So it kind of stops that fast diffusion, and they have to go slow in these points or go through the bulk or something like that. But we have a path where we get pretty good significant path of diffusivity. So there's a lot of other ways to describe boundaries, and we do a lot of these things, but I'm not going to go back to those. We're just going to focus on our distribution functions for now. But just recognize that you don't have all the information just because you have these nice functions that have all your crystallographic parameters. Right? There's a lot of other things we can do mathematically to describe what's going on in your structure. This percolation is a really nice way to look at stress corrosion cracking. If anybody works on stress corrosion, because it's almost always intergranular, and it's almost always your susceptible boundaries are the ones that are popping open. So it has a decision every time it hits a triple junction, you know, your boundary coming in, it hits that triple junction. Okay, which boundary am I going to take next, right? And it's a function of your stress state locally, of course, but it's also a function of your boundary parameters. Okay, that's just more percolation stuff. Okay, but the important part, which I've emphasized, you have 8 parameters available to describe the boundary. In this case, we're describing it with 1, and we can come up with some nice conclusions. All right, this is something in aluminum plate. It's called the hole expansion operation. Maybe if you've worked in aerospace or familiar with how they do wing spars, you have a thick plate of 7000 series aluminum. You get a hole drilled in it, and then they worry about fatigue around that hole. The hole is to join the structures, right? So you have to join to the fuselage box, and then you have to join the stringers to the wing spars and those types of things. So you drill holes through this thick plate product to have this huge spar. It's either 5 inches thick or 8 inch thick plate, right? So whatever that is in centimeters, right? 200. And then you want to improve the fatigue resistance, so you put a mandrel inside and you open it up, right? So you put it inside that hole and you just squeeze it out, and it hardens the inside of the hole, right? It's like a shot peening procedure or something like that. Sometimes they're starting to maybe use cavitation peening for this process, but it's a process that once in a while they'll have the wing spar completely machined out. They do the whole expansion procedure, and you get a crack, right, where you have an overlapping piece as in your mandrel as you're expanding, so you have a little stress concentration. And if that happens to hit at a certain place that's susceptible to cracking, you get a crack through the plate. Sometimes you get a crack, sometimes you don't get a crack. So if you look at the orientation map for this, these are large grains. See the 100 micron scale bar? It's a really thick plate. It's been hot rolled. And if you look at the boundaries that are cracking, you don't get very much information on if you're looking at trying to define special boundaries. You really don't have much information. But as you look at a rolled structure, you know all your grains are pancake shaped. So your grain boundaries are largely lying in the plane of the rolled plate, right? So most of your grain boundary normals are in this direction. Certainly the ones that are cracking, if I have my whole expansion here and we get a crack that shoots off on the boundary, then you can see, you know, the boundary is always going to be normal to that plate like that. All right, so now we look at the distribution. So now this is looking at the plane normals as a function of crystallography. So what we're trying to look at is what the normal to the grain boundary plane is in the space of the crystal lattice. We know as far as the specimen coordinate frame that they're all kind of lying in the plane, right? They're pancake shaped. But now we're looking at the crystal lattice and the orientation frame of the crystal lattice. So this is surface area per unit volume for crystallite orientations that are lying up against those boundaries. This is the entire distribution, this first one here on the left. The one over here on the right is only the cracked boundaries. You can all of a sudden see a difference, right? So now we're looking at misorientation. But we're not really doing misorientation, right? We're just doing what that orientation of that plane is along the boundary. Now, if all of our planes along the boundary, and we know our boundaries are all in the same orientation, then we know that we should see something in our crystallographic texture, right? Because that means all our planes are lined up in a certain way, or the bad ones are lined up in a certain way. So then we go back to the texture and we say, okay, we're just look locally, right? Because before we measured the orientations as a whole, now we're just looking locally. What happens locally where we don't have cracks near the hole and where we do have cracks near the hole? We saw something really interesting that we didn't expect by just measuring the overall texture before. And that was that in the cracked plates, we had a lot of brass texture. And in the uncracked plates, it had evolved to the copper texture. So FCC rolling textures, you get a distribution that goes along a line that starts with Gauss up to brass here. So it kind of goes along this line here from a point here, which is Gauss. And then it goes through the space up until you hit this position, which is copper. Right, so this is called an alpha fiber. The one that goes through the space is called a beta fiber. And if that's well developed, then we don't have cracking in the plates. So now we know how to process the material different to get more of these kind of uncracked plates, because we can process it so that the texture is going to evolve more rapidly. We're going to take a larger bite on our draft or our rolling. We're going to deform more for each bite. And if possible, we're going to deform it as much as we can, right? So start with a larger width ingot, or just do it at a lower temperature and higher deformation for each draft. Anyway, so that took us right back to copper by looking at grain boundaries. So this is one of the functions that I mentioned in that first slide, where the function is N and orientation, right? So that's the function we looked at. It took us back to texture. It was familiar enough that we knew how to change the process. So we ended up changing the process. And they actually patented this to say this is a way to stop hole expansion, cracking.
So it's a phi 2 and phi to 90 degrees, like 0 to 90 degrees. Brass is repeating. That means that if I go up to 180, brass will be in the same position.
Yes.
So it's just, in the respect means I can repeat even 0, 90, 180, and 360 will show the same brass component.
Yes. So when we talk about crystallographic symmetry, remember there's 24 points in Euler space that are all symmetrically equivalent. So there's 24 of those that will show brass. And then when you consider orthotropic symmetry, there's an additional factor of 4 times that, right? So we've rolled the sheet, we've rolled the plate, so we say there's a factor of 4. So because of orthotropic symmetry, this is the same as this, is the same as 180, 270, 360. They're all exactly this, showing the same components. That's correct.
These both are fiber texture.
Yeah, so FCC rolling, you go from Gauss to brass, which is a really nice, you can see that very clearly in your fiber texture. It actually also goes along this position. This one here is also showing an alpha, right? It's a symmetrically equivalent positions. And then to show the beta fiber, you have to start here with your brass and then come up to this point, just follow this intensity through. These are S textures as you're coming through here, all the way up to where your copper texture is. So brass and copper, or Dillamore component, is the 2 ends of your beta fiber. Yeah. Okay, so we talked about that, about how to play with the copper to brass ratio. Another example, this is creep-in copper. So we're looking just at pure copper. It's annealed. It's crept to 60% of its, at 60% of the melting temperature to 60% of its fracture life. And then you analyze the sections and say, what's the distribution of boundaries that get holes that pop open on them, right? Because in creep, you get vacancy diffusion that goes to the boundaries, and then you get the boundaries that break open from each other. So you can get a really ductile material like copper, and it can fail within about 1% strain, right? And that's because all these holes open and just breaks apart. All right, so this is looking at the boundaries that have been damaged. This is one dimension, of course, right? And if I take, this is just kind of an aside here, but if I look at all the boundaries that have been damaged and then I divide that by all of the boundaries in the distribution, then I get a fraction of boundaries that are damaged of a given type, right? So now I can come in and say, I have a lot of boundaries out here at 60 degrees, 50 degrees that are being damaged. So I might think those are the ones that are being preferentially damaged. But when I divide it by the overall distribution, I see that it's actually this group that is more preferentially damaged. Because I'm just dividing this function by the overall function, which looks kind of random like this, and then high that for twins in copper. So this would be the overall function, this would be the damage function, and this is the division of the two, dividing. Okay. All right, so now I look at boundary normal dependence. So we figured out where the grain boundary normals were on each of these. We did the same type of thing. And of course, as you would expect, but we're glad to show that the statistics show it, boundaries that are damaged are normal to the tensile axis. It's not a kind of a landmark kind of conclusion, right? You expect if you're pulling on something and you have that tensile stress across the boundary, that's the boundaries that are going to be damaged most. So we saw that. The tensile axis has boundaries that are damaged most. We went back, I actually thought I had a couple of more slides. We went back and looked at the ones that were damaged primarily on this. And surprisingly, in the MDF, so we looked at only those with this normal. So we said, okay, now we're going to just focus on the boundaries that are normal to the tensile axis. And it turned out that the sigma 3 boundary were the ones that were damaged the most. I was like, those are coherent twin boundaries, and I don't see any damage on my coherent twin boundaries, right? So then you go back to what's the plane of, in the crystallographic space, what's the plane of the boundaries that are damaged? And it was all in the incoherent planes, right? So the sigma 3 twin, the coherent one was not being damaged. The incoherent one was the one that was breaking first out of all the grain boundaries, right? So that one has a better story that I just skipped. All right, what if we're worried about deformation? Right now you have to think about slip transfer. So you have a slip, a Burgers vector B on a given slip system I in grain A, and it's going off into a slip system B sub J in grain B over here. So that's a grain A. This is the boundary. This is grain B. Looking at the slip systems, there's a lot of different numbers you can come up with that are called a slip transmission factor. This is a simple one from Shen, Wagner, and Clark. Seems to be the one that works the best, where you just take the dot product of the lines of intersection of the slip plane with the grain boundary plane and the dot product of the two Burgers vectors. Multiply those together. So if the grain boundary plane was through here and the slip system was exactly the same, this value would be maximized, right? Because they're all parallel to each other. So if they're not parallel to each other, this number goes down, we get less slip transmission. So now I'm just showing a simple experiment. This is supposed to be a bicrystal. We have a single crystal on top, we're deforming it in channel die, but what we do is we look at the surface where the bicrystal is, we deform it, we look at it again, we deform it, we look at it again. We're trying to see how slip is occurring across that boundary. So this is 0, 5, 10, up to 30% slip. This noise up here, that's a fiducial mark I made with a Sharpie pin, right at the top of the boundary, because I wanted to measure the same position each time. And you just see how the orientations are starting to change, and you get some local things going on down here, right? Now, if I'm worried about grain boundary in this is just showing how the misorientation changes. So that's 0%. By the time we get to 30%, the misorientation angle right at the boundary has reduced quite a bit. This doesn't always happen. It just happened on this specific bicrystal. And I didn't talk about the orientation of the bicrystal. This is one that we picked up from the other experiment. So this was an incoherent twin boundary that we were looking at. Okay, this is an incoherent twin that we're doing deformation across. So they're rotating towards each other, those crystallites. One of the things that if you look at the surface, you start to see slip lines on the one crystal, and you see those slip lines on a shared plane, right? It's a twin boundary, but it's incoherent twin. So this is the, how did we have it here? Blue grain was on the left. So this is the blue grain, this is the yellow grain. So you can see what the blue grain orientation is with these blue dots and the yellow grain, and there's one shared because a twin boundary is 60 degrees about 111. So if we do a 111 pole figure, then one of the axes has to be shared. But in the grain on the right, this yellow grain, we start to see additional slip that's happening in there instead of just this primary slip band that's shared between the two. The other thing you'll see, this isn't a nice straight boundary, right? If you look at that boundary, you can see the jog in it. And the reason is the incoherent twin is not a nice stable boundary like the coherent twin boundary, which would be a nice plane that we are looking at. So it's not stable. So this was a diffusion bonded crystal. We did diffusion bonding to make that type of a boundary that we wanted to look at. And it's, that's what we got, right? So we can make the boundary, we can force it to have that boundary, but it doesn't want to be there. If we look at the Taylor factor evolution, even though our misorientation is getting less at the boundary according to the exact angle, the Taylor factor actually is starting to split. So the Taylor factors were pretty similar for the plane strain deformation we imposed, and at the end they weren't. And you can see, this structure here, that's dividing, that's starting to subdivide that grain. Then we did some modeling. I'm not going to talk about that, but this is from crystal plasticity modeling. A lot of the stuff that Dr. Misarovich is talking about is how we did this. We modeled what was going on, but I like this one specifically because it shows, this was supposed to be a nice bicrystal that we made with the high energy boundary. And what happened during the diffusion bonding process is we nucleated a couple of new grains on that boundary. So we have a twin coming in the one side, we have a couple of new grains that are nucleated. This is pretty local. These are small grains that we would see along the grain boundary. The other one, these are 15 millimeter wide, this bicrystal, and we're looking at 9 microns here for this. So we have some little grains that start to develop. But this was after deformation, and what's interesting is there's places where you have, if you look at this bottom grain, this small grain in here, you see these twin boundaries that are along here. You see the deformation that is transmitted to the neighboring grain. So through this region, we get one type of deformation. As soon as we get this new orientation that develops, we have something else happening. So that grain is being affected by that slip transmission. Now, the only way I can describe all this is from 8 parameters of grain boundary, right? The entire grain boundary function. Because I need to know what my stress state is, need to know what the grain boundary is, the normal as well as the misorientation. So I need all that information if I'm going to come up with some kind of statistical information here. Okay. And then I just make a comment that it would be much more interesting with these triple junctions if we could figure something out about how to describe what's going on there. And so that's something we haven't played with yet. All right, a couple of final considerations. This is one we've talked about already. There's indexing problems at grain boundaries. If you're doing EBSD data to determine what the boundary is, and that's because you get this destructive interference of one pattern in the diffraction from this grain, the diffraction from this grain, you put them together and you get a confused pattern. So you have to deconvolute those, that information. It works pretty well, right? This is one with no cleanup. I haven't altered the data at all. I've shown you this one before. This is image quality up top. This is confidence index down here. And so these points along this boundary are low confidence. So I could just throw those away because I'm saying they're low confidence, but they actually are the same orientation as the grain. So I'm saying that's probably right. So I'll do a grain confidence index standardization and clean those up. And then I have these points here, and I have to decide if I'm going to believe those additional points along the grain boundary. If I want good grain boundary statistics, and the points that are wrong typically are at the grain boundary, then I'm missing a lot of the data that I want. What I would do in a case like this is I would define grains as being large, a lot of points together. So these points are not defined as grains. And then I would do a dilation cleanup where I would just squeeze my boundary together. Right? I just say, make this red and blue touch each other everywhere. And then I have all the information. And in my distribution, I'm not going to get a misorientation that is between this light color. Wow, nice. What did I do? Nice. Something happened where it drew a circle. It was a surprise. Anyway. So yeah, I did it again. Huh. Cool. I didn't know it would do that. Anyway, so now I'm cleaning those up, right? So I tell my students, never clean up, never clean up, never clean up. Sometimes clean up. Sometimes clean up. If it's for specific boundary statistics, I would never clean up for texture, right? Because then I'm creating new data. For this, I'm just plugging the holes on the boundary, but I still have to tell the computer what's true, right? So here's another example. Here's some where I have a couple of points on the boundaries, right? You can see maybe they're real, maybe they're not. We decide they're not real. We tell it to clean up. It just fills those in, right? So now you get boundary statistics from the clean data versus the raw data. And you just have to be careful. If you ever clean up the data, and even if you ever don't clean up the data, you should always report that in your thesis or in your papers you write. Right? So in the EBSD community, they have these meetings every year, every couple of years, the EBSD meetings. And one of the things that they've emphasized constantly is always report if you're cleaning up or if you're not cleaning up. Right? So always put that in your paper. Say these are the raw data, I haven't done anything to them. Or these are data that I've done a single iteration dilation, so the boundaries will be all, I can get better boundary statistics. You have to put that in.
Those points in the boundary on the previous slide, they look like almost periodic.
Yeah.
Could those be green boundary dislocations?
I mean, grain boundary dislocations you won't see in EBSD, but if you have dislocations that accommodate the misfit, it could further interrupt the diffraction that's there, and so you might have lower quality diffraction at specific points, and they turn out to be a specific, they turn out to give you a specific value. The thing that is concerning about these is they're all the same color, right?
Yeah, but
So I say it's mistem. I say it's just mistem. It's a coherent twin boundary. It's just mistem. But
if there are dislocations, they would be the same.
it would look the same, but it wouldn't be a different orientation, right? You shouldn't measure a different orientation. So, all right. The other thing it could be is some kind of pitting, some kind of etch pitting, which you get a really strong contrast. If your beam goes down into a pit, you get a strong contrast with that. And sometimes that strong contrast will give you the same orientation everywhere. So if there's pits along the boundary from the polish that you've done, then you could, you might see something like that. That's another thing that it could be. Okay. But this is something I tell people to do for boundary statistics, but I also say be really careful because you're just inventing data, right? You have to recognize that you're making stuff up, okay? It's not what the instrument gave you. It's not what's measured. It's you've looked at it. You've done maybe some other type of analysis and said, okay, there's not grains there. I'm going to clean this up. So you have to justify it.
Why not to decrease the step size? By decreasing step size,
Yeah.
you minimize the error.
Yeah.
And then it's much better than averaging. So,
Maybe. I mean, if you do very small steps, maybe you'll just get a lot more bad points along the boundary because you'll be taking a lot more points on the boundary. And the other thing is boundary statistics, right? You want hundreds of thousands of boundaries. And so smaller step will just take a lot longer to collect and a lot longer to analyze. So there's always a trade-off. But that would be one of the options, right? Especially if there's small grains in there, you'll see them now with smaller steps. Okay, so just going back again to show how we describe the boundary. Different parameters, we have the planes, we have the orientations, we have misorientation, we have an external reference plane, so there's a lot of options. Now, what if we have these types of things? Curvature, faceting, specific type of misorientation that will occur. So those are things that I haven't included in any of my functions. I could include how the boundaries are connected, percolation, connectedness of the boundaries. A lot of things here that aren't included specifically in that. Here's just examples of different types of structures that would be particularly problematic for doing grain boundary statistics, right? If you have a highly deformed material like this one, it's really hard to even define a grain boundary using EBSD. Because you say 15-degree boundaries and they're going to be discontinuous boundaries everywhere. It's not even going to create a nice cell structure. Okay. Okay. Grain boundary planes. I'm just checking. I think we're supposed to take a break at 10, right? Is that what we kind of usually do? And then come back and finish. I think last time maybe I did a little bit early on the break, but more or less how we do. Okay, boundary planes. So we've talked about how to measure boundary planes a little bit. So 3D serial sectioning is the obvious way to do it, where you actually get three-dimensional data. Takes a long time, takes specialized equipment, but it can be done. It really decreases the amount of grain boundaries, the number of grain boundaries that you're looking at, because you have to do orientation maps, maybe 20 orientation maps for that boundaries, for that set of boundaries on your map, right? So you have to do a lot of planes, see where the boundaries go, and then pull out the normals. So we can do it along a corner if we have two polar surfaces. That's something that Val Randall did a long time ago. But mostly what we're doing now is using a single plane and using these stereological tricks that we've talked about. And then we're plotting these boundary up in a space like this. So it's a stereographic projection. This is showing the planes of boundaries for a fixed misorientation. This one is likely, the boundary plane is mostly along a 111 crystallographic plane. So I'm just going to guess that this is a sigma 3 boundary, right? 60 degrees, about a 111 axis. And then that's showing where the boundary is. Most of them are coherent boundaries for this misorientation. Now I have other misorientations in my distribution, but this plot applies specifically to that misorientation. Right? I could do this with, let's say, just show me 60-degree boundaries, and I could ignore the 111 axis rotation. Then I could still come and get this type of a plot. Or I can show the overall distribution of boundary normals. Right? But this one, what's typically done with the 5-parameter description, you fix a misorientation, or delta G we call it, right? You fix your delta G, and then you plot N for that delta G. Okay, so that's what you're looking at. If you ever see grain boundary plots that look like this, they're plotting the grain boundary plane. This is a button in the software, right? So you can go and use your OM analysis software and create these types of plots. Remember statistical reliability in grain boundary space. We're now talking about 5 parameters that you're using, right? A misorientation plus a plane. So you should have 10 to the 5th measurements of grain boundaries to get acceptable statistical reliability. I don't mean 10 to the 5th, I don't mean 100,000 EBSD points, I mean individual grain boundaries. Right? So maybe you're measuring 100 points for every grain boundary because you're getting 50 points in each grain that makes up the boundary, something like that. Okay. And that's not exactly true because a grain has more than one boundary, but you know what I'm saying. Okay. Representation of these functions. So I've mentioned that these can all be represented in a Fourier series expansion. Now this is looking at surface area per unit volume. This is looking at line length per unit area as a function of angle of the boundary. So this is the function that we want. This is actually what this gives you. Right, that's an S sub V as a function of N. That's what this plot is. Surface area per unit volume as a function of grain boundary normal. So the boundary normal is being shown. But the measured functions are line length per unit area on a plane section or intersections of a scan line with a grain boundary per unit length. That's points per unit length right there. They're all represented in Fourier series. And in the mathematics that's developed, we can use these coefficients to come up with the desired coefficients. That's the stuff I just talked about briefly before. We can also add crystallographic dependence. So now if we want S sub V as a function of N, we can add in orientations, A and B, or we can add in delta G, A, B, something. Right? We can add in whatever crystallographic dependence we want. So that fits now in our stereological equations, and we can put that directly back into those summation equations that we put here. We just have to add, remember now, these T functions, LMN, and what I'm calling the Y functions, which are PQ. So this is G, this is N, this would be delta G, I guess. Okay, just multiply this on, and then we add the other indices onto the coefficients. Okay. All right, a couple of other things to concern ourselves about. Let me just check a couple of things here. Yeah, I'm getting close here. I'm getting close. Are we about where we want to take a break, Shomjit? We want to take a break at 11?
We can take a break now.
Should we do that, and then we'll come back and finish the discussion? Okay. Okay, good. This is a good time to stop. How are you? Good. Yeah. Have you been there?
Yes, sir.
Have you been to Jakarta? Did you visit before?
No, sir, no.
Yeah. Well, that's very interesting.
Good place.
Yeah, the jungle's nice. There was,
After food.
yeah, food was good also. Yeah, we stopped at this place that Shampa had suggested.
Okay.
So we saw her and she suggested a place, so it's close to some of the castles and temples we saw.
Okay.
Yeah, there's a big menu, a lot of things to choose from. Well, we did family style, so we would choose stuff and then put it all in the middle, so we all took a bunch of, like a buffet kind of. It wasn't a buffet, but we ordered a bunch of dishes. So
Okay.
we had some fish, and we had some kind of cheese paneer type thing. I don't know if it was paneer, but some type of thing that was close to that.
Okay.
We had some kind of chicken dish. Had some, what do they call it, jeera rice, something?
Yes.
हेलो 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 चेक हेलो चेक आ रहा
Oh, that was fun. That was fun. We were seeing lots of interesting things.
মোটামুটি ক্লিয়ার আছে তো এখন হ্যালো
Check my stomach.
হ্যালো
Not that so far. So, well, I feel it and I feel I shouldn't be entering things for a while.
Okay. Thank you. We're back here. All right, so going back to what we see on a plane section, right? Because most of what we do with metallography or materialography, as people call it these days, is to look at plane sections where we're examining what kind of features we see. So when we see boundaries on the plane, we see these lines or these curves between the grains. And this is showing if you look where the blue line is here, whoops, I'll do a pen instead of a laser pointer. If you look where this little blue line is, coming up through here, and then focus only on this boundary, right? So we're focusing on that boundary. So this is a two-phase material, so we have a hexagonal phase and we have a cubic phase. And we look at that and we say, what is the crystallographic character of that plane, of that boundary? So a boundary is an area, right? It's a plane or a part of a plane that we're looking at. It's a surface. And so if we look in the alpha phase and we say there's how that's oriented, then we only know one trace in the crystallite of what's happening. So we know the orientation of our cube on one side of our cubic lattice. We know the orientation of the hexagonal lattice on the other side. And we know where that trace falls. So if we're saying, is that a 1-1-1 plane that forms along that boundary? We don't know, but we can look at the trace of the boundary and say that's consistent with where a 1-1-1 might be, right? So you have the trace or a line of a boundary like this, and then underneath the boundary can be any of these orientations. So that's what this is showing on the stereographic projection. So we have a trace that is consistent with it being a basal plane that forms along the grain boundary, but it could be any of these orientations along the grain boundary, right? So this is just what plane lies along the grain boundary. So it might be the basal plane because your hexagon's there and our line's there, but if you rotate it like this, it could be anything in that from a pyramidal plane up to a prismatic plane. It could be any of those. And so we don't know, but we know it's consistent. So if we expect to have a basal plane there for certain types, we could check it and say that's consistent with what a basal plane is. On this one, we look and say maybe it's a 1-1-1 where the FCC or where the cubic lattice is. So it's consistent with 1-1-1 over here on the cubic side. But again, we have this entire arc. It could be, 360 degrees. You don't have to stop that one there. This one could keep going as well on this side. It could be anywhere in there, that boundary plane. It could be oriented in any of those positions. But if we see this, then we say, okay, this beta phase, which is an FCC phase in cobalt, is consistent with a 1-1-1. The alpha phase is consistent with a basal plane. And when we know what the transformation is, we know an orientation relationship in cobalt, which says your 1-1-1 plane in FCC will align with the basal plane in HCP lattice. So that's what we expect. So if we have this start to transform, if we're transforming from the high temperature FCC phase and down into the low temperature FCC phase, then as it starts growing, it's going to grow so that the basal plane is aligned where the FCC 1-1-1 plane used to be. So that's what is being shown here. So we don't really know it's 1-1-1 in basal plane, but we have a theory that says it is, and then we say that trace means it's consistent with that, right? Even though we can't do the actual measurement, a lot of times we'll say, okay, that's a 1-1-1 plane and that's a basal plane because of other things we know. So we've talked about measuring things and serial section and doing stereology, which takes a lot more mathematical effort to get. But you can also just be smart sometimes about it and say, I know what plane is with both of those boundaries because I know what the orientation relationship should be. Same with coherent FCC twins or coherent twin boundaries. You see the nice, long, straight twin boundaries. You know what they should be. You check and make sure it's consistent with that. And then you can say, go ahead and say that's where my plane is for those boundaries. Okay. Even though you can't completely confirm it experimentally, you can confirm that it's consistent with what your expectation is. Okay, data cleanup. Always have to be careful with data cleanup. Now, I've shown you this before. This is interconnect lines of copper. So the nice copper lattice, so it's 111 with some 511 twins. That's what those pink grains are. And then in between here is dielectric. So those are amorphous material. That's amorphous. And so you measure your EBSD map and you throw away bad confidence data and you get this one in the middle. All right, looks pretty good. So you're happy with that data. But now you say, okay, I want to clean this up. I want to make sure I have all my boundaries tight together. So you do a dilation cleanup or something. One way you could do that is just say dilate till it's complete, right? Dilate it until my whole space is filled in with things that I define as grains. And if you do that, you come up with this last one, which is not good, right? Usually X means not good and check means good. This, this one's not good because all of a sudden I've created a bunch of new boundaries along here, right? So now all these boundaries are going to be in my distribution. So you have to be careful when you're doing cleanup that you're not creating all these artifacts in the data. So that's why I always say don't clean up except for grain confidence index standardization that I've told you about, where it just makes all the points within a single grain, what's defined as a grain, turns all those high confidence so that we can save all those data when we do a confidence index filter. But if you do a grain dilation cleanup or you do an orientation correlation cleanup or any of these, then you can create artificial data. One of the beautiful things about that, which is really not beautiful, is you can have an entire data set from an amorphous material like this dielectric, where it's all just speckled everywhere. And then you can use cleanup strategies to get a nice perfectly equiax data set, right? You can have nice grains defined, just completely artificial data. So always be careful with that.
What is grain dilation cleanup?
Grain dilation cleanup is where it defines a grain as a contiguous set of points within a certain tolerance angle. So, you know, here's 20 points that all have the same angle as each other, and you step grain to grain, and your misorientation's not greater than 15 degrees or whatever you define as your grain boundary angle. And then it defines all the grains and says, okay, these are defined as grains. But there's a bunch of single points or a bunch of bad points that are not defined as grains. So you say grain dilation. So it effectively takes each one of your grains and it increases the border by one step size in your scan. So it just dilates it out, right? So each grain grows by one dimension around the outside. It doesn't grow into other grains, right? It stops, it doesn't grow. It just, if a grain isn't defined in a region, then the grain will grow into that. So in this case, we have this black region where nothing's defined. And so these grains here can just grow straight across, which you see what they've done here. Although that green is kind of interesting because you see that tiny little green point there? Somehow that was left in as a grain definition for that. So that green one started to dilate and started to grow before the blue one came over and impinged upon it.
The black one has gone. The black one has gone completely.
The black?
The black line?
Yeah. So black just means there's no data there.
There's no data.
Yeah, no grains are defined in those regions.
So the colored one has dilated.
The colored ones on the right side have been dilated to fill in the space where those grains weren't defined, right? And in this case, it creates an artificial structure. If you have a nice, fully dense material that you don't expect any holes in, Maybe you're just going to have a few missing points on the boundary, then it's okay to dilate and clean it up. If it's completely crap to begin with, go get better data, right? Don't do a cleanup and try and clean up some really bad data.
But cleanup has to have some strategy, like dilation is one method, but we have to define criteria for cleanup.
Yeah, there's probably a dozen ways to do cleanup, because as we started to figure out how to do these routines, we consistently said, okay, well, let's say, you know, if we have a hexagonal grid and we have 6 points around it, around a given point, and if 3 of the points are the same orientation as that one, let's make this one the same as those other 3 points, right? So that's called a grain orientation cleanup. And you can say it have to be that orientation, plus they have to have that confidence index. And so you can use orientation plus confidence, or just confidence, or, you know, there's a lot of ways to do it. And you can say, let's say only 2 data points have to be the same as the one in the center to clean it up, right? So there's a lot of options. A lot of ways to create fake data. That's what it is. So be careful. All right, pseudosymmetry. There's a lot of times where we will have data or materials that have, let's say, an A-axis and a C-axis, so a tetragonal symmetry, that's very difficult to distinguish from each other for some reason or another. If you look at Y123, so a superconducting material, the C-axis is essentially 3 exact, if you take assume Y123 is a cube orientation, if you take that cube and you stack 3 of them on top of each other, then it's effectively the tetragonal lattice. Now the reason it's not just cubic is because there's one atom in alternating cells where it switches position. So in the bottom position you have an atom, and then it switches position in the next cell, and then the next one it switches back. So you need all 3 of those cells to call it a C-axis. Diffraction is almost identical between A and C-axis. There's only one different band in your structure. So you have all the same Kikuchi bands except one, and it's not a strong band. It's one of the lower order bands that is harder to see. What we're going to look at here is something called lead zirconate titanate, where you have a BCC type of a structure. I shouldn't say BCC, I should call it zinc blende structure, right? It's got a different atom in the center. And that atom, when it's polarized, when you magnetize the material, it shifts from the center. So it's not exactly in the BCC position, it's not in the center of the cube, it's shifted off a little bit. So then you have a C-axis and an A-axis based on the shift of that center atom. But the magnetic properties are very different in the A-axis and the C-axis, right? So your properties are different, your diffraction patterns are almost the same. So what happens here for that kind of situation? This is just showing 2 situations where the A and C axis look very similar to each other. You can see the pattern. The one on the left is indexed for an A-axis orientation, right? So it shows 010 here in this position, whereas this one is showing a C-axis in that position. And if you look at all the bands, you say they line up pretty good, right? All of them line up pretty good. Even though they're different, they have different properties in the A and C axis. So here's the lead zirconate titanate I'm talking about. We have the lead and the oxygen, which are always in the same position, and then the titanium or the zirconium atom, which is in the center, and it will displace a little bit to make a tetragonal lattice, right? So then you have a C and A that are different. Okay. All right, so what's the difference in the patterns for those? If we look at this one specifically, it's showing the black lines, which show you where a C-axis orientation would be, and the white dashed bands where the A-axis orientation would be. And so they shift a little bit, right? You can see some difference in there. but a lot of them are very close to each other, and if you do standard Huff indexing, it's going to be really difficult to determine the orientations. So what does your map come out like? You get this speckling, that term in quotes there in the top bullet. You get a speckling. So you'll have a grain. Maybe I'll look at this grain here. It's a green grain, but then you have all these kind of orange points in it as well, right? And one is a C-axis interpretation, one is an A-axis interpretation. And they're both equally probable, right? They will have the same confidence. Basically, you'll have 0 confidence if you put both those different phases in, because it will say, it looks, you know, you have 30 votes for A and you have 30 votes for C. So that means the top 2 solutions are the same, so you have 0 confidence because you subtract those from each other. So you can't go in and just use confidence index to clean the data. A lot of times when this happens, if you look at a misorientation angle histogram, you'll get a huge peak at a specific angle. And in this one, the C and A axis are 90 degrees rotated from each other. So we have all these grain boundaries that we define. In this grain that we were looking at, between the orange and the green, those are all 90 degrees apart because that's what the pseudo-symmetry is. So it's just wrongly indexed. And you can look at, you know, other examples in here where you have, you know, this grain here where you have the blue and the maybe fuchsia, whatever you call it, something like, you know, all those are all over the place. So we have a high peak in our misorientation angle histogram that says it's 90 degree rotation angle. If we calculate the misorientation distribution for that 90 degrees, they're all oriented about 100, right? So we're getting a 100 rotation, and that just transforms A into C, right? 90 degrees, about a 100 axis is just transforming A into C axis, C into A axis. So these data that we have these nice sharp peaks in, that's fake data. That's not real. Those are artifacts of the pseudo-symmetry that it doesn't allow you to index it properly, right? So it's fun to see sharp peaks in your data because then maybe you can define what's going on and figure out a different way to process and get the material better. But you have to always be careful with what your material is and if it's correct or if it's incorrect solution. Yes?
But we can't avoid it, right?
So the question is, we can't avoid it. So that is actually true. This is a really sad one. You can't avoid it. So what do you do? Right? That's the question. What do we do? So there's a couple of tricks we play. One is we can come in and we can say, let's assume everything's cubic. Right? Then we get nice grain structure. We don't have all that speckling. This is the same data as the one we showed here. Nice data. All of a sudden we like it all. It looks correct now. But now we can't distinguish which is C and which is A. We don't know. And if those properties, if we're looking at that magnetic domain in lead zirconate titanate, we can't determine that. So we have to determine by some other method what's going on. So one of those methods would be if there's a mechanical property difference between C and A axis, which happens really nicely in the superconducting material, the YIBCO material I was telling you about, the yttrium-based superconductor. If you go in and you do nano indents inside where you did the EBSD scans, then you can determine very nicely if that was an A or a C axis. So then when you do your cleanup, you can go in and there's actually a way to manually select portions of your data. You can manually select portions of your data, make sure it all fits the right position, and then you have a clean data set that you can use. But it's taking experimental data, manipulating it based on what you have learned from outside, and then creating a clean data set. The other thing you can do is say we need to throw out all of these 90 degrees 100 boundaries. Okay, so you go in there and you find those, you say what the orientation relationship is, so you know what the orientation relationship is. And then you can go in and you can throw out the ones that are speckled inside the grain. Problem is, again, you don't know if you're throwing away the right ones or the wrong ones, right? So you can't tell if you're doing that. So the work that is being done recently using dictionary indexing and spherical indexing is one way that you can determine very small shifts in the pattern, and it has actually shown to be very accurate in determining things like lead zirconate titanate. So we can use dictionary indexing, use spherical indexing, and then we can do it. Now to do that, you have to save all your patterns as you collect the data set, and then take it to the software that will allow that to happen, which commercially it's OIM9, which we don't have here right now. But if you use the data that's in GitHub, the EM Sphinx, which will take you about a week to make that run properly, but you can get that running and then you can do it using that if you have one of these difficult types of materials. And that's what I would recommend. I mean, you can play with this kind of a thing and try and get it, and it works pretty good. But using a dictionary or a spherical indexing strategy would be the best strategy for this.
What pseudosymmetry means?
Pseudosymmetry means it basically looks like it's symmetric, but it's not.
Okay. There is a pseudosymmetry means like mirror planes, rotational axis, these are symmetry elements. So in pseudosymmetry also there are symmetry elements?
So the question is about pseudosymmetry generally, so in what I'm calling pseudosymmetry. So for me, pseudosymmetry will have all the elements, or effectively all the elements of the symmetry group. Right, so if you have an octahedral group for cubic symmetry or something, it's going to have all 24 of those elements of the symmetry group. But they will be slightly shifted or slightly different, or maybe one additional band that will break the symmetry. But for the most part, all those symmetry elements will exist, at least as far as we can measure them using a Huff. Yeah. So these things just happen, and we figure out ways that we can actually interpret it. But make sure you don't look at something like this and interpret it as peaks in the function, right? So make sure if you come up with this against this kind of a problem that you can use additional techniques, additional strategies to get around the issues. Is anybody doing anything with stuff that they would say is pseudosymmetric that's difficult to index A to C axis or something like that? Not right now? Okay. The supercell, yeah, that you asked about. Yeah, the superlattice is another similar type of an issue. Has all the same symmetries.
So that would be also considered pseudosymmetry?
You could consider it in the same definition that I call this pseudosymmetry, right? Right, because you just can't determine what the superlattice is compared to the original lattice. That's right. Okay. So this is just another one talking about deconvolution of that. Let me see if I should be about through the slides for this. And then this is just showing what's happened after it's been. This is the one with the indexing problems. This is the one that's been deconvoluted. And if you look at your material, your misorientation distribution functions, they look completely different, right? Because this one includes all the errors, includes all these white boundaries that we don't believe, and this one doesn't. Okay. So this one is just wrong, even though that's what's measured directly when you're doing the indexing. Yes?
Is it clean? Deconvolution means?
This has been deconvoluted to where we took these white boundaries. We said anywhere we have these 90-degree white boundaries, let's reassign the orientation of all of those to the major component within each grain. Okay, so for this grain, there's orange and blue, but there's more orange than there is blue, or more yellow than blue. And so it would assign all these yellow ones to the blue, or all the blue ones to the yellow, I'm sorry. So the grain looks like that afterwards.
So it can be cleaned also, right?
And then it could be cleaned additionally after that, right? So this is fixing the pseudosymmetry problem. So that's one of the cleanup routines is the pseudosymmetry. And then you go in and you can do a dilation or something after that. Yes, another question.
So that is in terms of orientation. What about like once I do the convolution, one of the faces, if I want to do my face map, one of the faces will disappear. Because we are saying like these particular 90 degrees are not useful. Means we're kind of just removing them. But that is coming from the other face, most probably.
Okay. Yeah, so the question is, doesn't this just make the C-axis oriented grains completely disappear, for example, or if it's a second phase with a superlattice, maybe it completely disappears. So in this case, in the case of where we reassign them to cubic, like this one, it disappears, right? Now all we have is cubic phase. In this case, it reassigns them to whatever the majority was to begin with. Right, so if we have this big grain, this big peach color grain in the center, the majority is already peach and it's gonna stay that. Whether it was interpreting the C-axis one way and the A-axis one way, it would keep whatever that interpretation is. So it doesn't completely get rid of it like reassigning it to be cubic everything. But again, you're not exactly sure that it's done the majority of the points in the way that which would be correct. So that's another thing to check
But
as
ultimately
you're
the fraction will be lower than the real raw data.
within the grain, yeah. Yeah. So that's how it's reassigned. Right. Yes.
Suppose there are two covalent phases, like one is my FCP, one is say a superlative phase. So by taking which phase I should index my data?
So the question is, what if there's two phases that are both, that either one could be used? You use the example of a superlattice, right? So we have the conventional lattice, and then we have one that would show a superlattice, a phase that would show a superlattice. Which one should we use to index the phase? Now, if there's an additional band that you would find in the superlattice phase, probably you could use both phases. Right, so you add the additional band, you use both phases to do the indexing. One thing I did when I was working on the superconducting material, the additional band that was there, I forced it to find that additional band. I said, if you don't have that band in the lattice, then find more bands, right? So that was an additional thing I put, which isn't standard in the software, but it was an additional thing that I put that I said, if that specific band is not there, then it has to be there because that's the only one that tells me the difference between C and A axis. And so I forced it to, okay, let's go find that band. So that would be a strategy, just technically how to do it, but as far as in the software itself, the only thing you could do is add more bands, and so instead of indexing with 7 bands, use 12 bands or something to index. And then you would have a higher probability of finding that one band that is going to tell you whether it's a superlattice or not a superlattice. Okay.
So it is in ordered structure. For example, FCC can be disordered and it could be ordered. So superlatives can be said only when it is ordered. It is.
So we're just talking about definition of superlattice now and whether it's, if it has to be an ordered structure, it can be a disordered structure, right? For the superlattice. So typically you're right that it would be somewhat of an ordered structure, but if you consider something with a lot of solutes in there, it doesn't necessarily have to be an ordered structure, but usually it's one specific type of atom that is breaking the symmetry or giving you something different. And it's usually in a specific position within these additional cells, like what I was describing before. So usually that's what gives you that superlattice structure.
So superlative has less symmetry than the disorder.
In every case I know of, it does. So the question is, does the super lattice have less symmetry than the original lattice, or the primitive lattice? And to me, that's a true statement, but I don't know. A crystallographer might argue with that. I don't know.
Is it possible to identify by the band, like by the spacing, like even if it's like the superlattice of a particular crystal structure, my D spacing will be either biggest, in this case like bigger. So with the superlattice, we can identify by that, but can we differentiate somehow? Because
Yeah.
even if the Kikuchi lines are superimposing, the bandcut will be different. Like the cone, the spacing will be changed.
Yeah. So the question is, can we use bandwidth differences in indexing to determine whether there's a superlattice or not? So there is an option in indexing to use bandwidths, and what that does is it checks relative bandwidths. So measuring d-spacing is not possible. Well, it's possible, but it's very uncertain, right? So you could measure d-spacing to within 10 to 20%, something like that, which is not enough to do anything, right? So you could use relative bandwidths, and maybe if there is something in your superlattice that says this band's going to be wider if it's a superlattice and more narrow if it's not a superlattice, then you could define that in your phases that you use and use that as part of your indexing. So I haven't tried that one actually, but if you have a band that would define well like that, then maybe that'd be a reasonable approach. Typically when I've tried to use bandwidths, it hasn't worked very well. So, okay, good. So we were at the last slide anyway, so that's just the summary of what we've talked about. Any final questions? It's actually 11:03. I've taken 3 of Sanish's minutes again. Any final questions before we wrap up? No. Good. We had good questions during the discussion anyway, so I appreciate that. Thank you. Okay, Professor.
Thank you. So last time we have started our phase field models. Before I briefly review the main ideas, let me remind you, why do we want phase field models? Well, we want to deal with interfaces which are moving, and then we have topological discontinuities, well, coalescence of domains and breakup of domains. So, and there are two problems with that. First is, well, theoretical problem, how to deal with the kinetics of an interface, and second is computational, how to track interface motion, and particularly how to do changes in topology. So, we need phase field models. Second thing I would like to remind you is that what we concluded from our studies of governing equations and continuum mechanics is one simple conclusion. If I can write energy balance, I have everything. From energy balance, I can derive my governing equations. Now, governing equations still need extra constitutive laws, which we will need to assume. But I can get proper thermodynamically correct governing equations just from energy balance or power balance, if you want. So, in defining our phase field model, we will use simple mathematical trick and we will work on energy because everything follows from there. And here's the simple trick. Well, if I have two domains, right, 1 and 2, for sharp interface model, my energy is energy density in 1, energy density in 2, integrated over 2 volumes plus interface energy. Well, instead of making this sharp mathematical line, I say there is a phase variable phi, which gradually transitions from 0 to 1 within certain interface thickness, h. And then I can pretend that this is all one domain. I have no more surfaces in this domain. It's all volume. And I can write my energy, well, as f of phi, where f takes value for domain, well, for the left domain when phi is 0, it takes value for the right domain when phi is 1. So that takes care of those two integrals, approximately. And then I replace my interface energy by a term which exists only where gradient is non-zero. And because it has to be positive, I take the square of the gradient. So this is gradient dotted. Gradient is a vector, right? Dotted by itself. Sorry? Phi, f or phi? Phi. Phase field variable. Something I dreamed up. I said I will introduce variable which is 0 here and 1 there. If, say, you are looking at the motion of say, a liquid surface, my phase field is 1 in liquid, 0 in gas. That's all I'm saying. Okay, now, in between those two variables, well, something will happen, right? I will have a barrier. But you can see that this can be made quantitatively equivalent. If I take a limit when h goes to 0, this will give me some finite value which will correspond to this interface energy, and this will give me effectively two domains, right? It will integrate this constant value f1 on the left and constant value f2 on the right. Whatever parameters I have, modulus of elasticity, diffusivity, anything that is material parameter can be interpolated, so which takes value 1 when phi is 1 and takes value 2 when phi is 0. Simple linear interpolation. Okay, well, I introduced some new parameters here. Let's see how those new parameters match with our known physical parameters. Here, last time, we have shown, and I have skipped some steps, right? I don't want to overload you with math. One can derive that this parameter here, kappa, which goes with the square of the gradient, and this maximum delta f here, when I write this delta f is this difference between, this is the function delta f, right? And this is delta f maximum. So if I take that to be fourth order polynomial, well, double well potential, well, I will get relationship between this delta f max, this one, this kappa, interface energy gamma, and the thickness of the interface h. So how should I proceed? I have, let's assume that I have interface energy. I will decide what my interface thickness will be for this particular simulation, and then I have my phase field parameters. Okay, now, well, these calculations presented on this slide are essentially one-dimensional problem. I take semi-infinite solid to the left, semi-infinite, or liquid, semi-infinite material to the right, and their interface at 0, at x equals 0. So, and I thought that many of you have been somewhat overwhelmed with three-dimensional continuum mechanics, which I have been droning on for whole 3 lectures, right? The tensors and everything. So I thought that you might appreciate a simple one-dimensional example. So, well, here's what I'm going to do now. I'm going to go over a paper. Well, it happens to be my paper from the literature. Not because it's mine, but because I couldn't find better example of one-dimensional problem. Sorry. So sometimes we can formulate problems as one-dimensional problem, and this, I think, because it's one-dimensional, I suspect many metallurgists and material scientists here had problems with tensors, and tensors we need for 3D and higher dimensional problems, but we don't need tensors for 1D. And here's our well, 1D problem. I will only qualitatively go through that paper, but you have that paper now, has been uploaded, and I urge you to go through it because it's a very simple one-dimensional problem, but it also has some interesting twists. So here's the problem. We are bonding zirconium carbide, 2 pieces of zirconium carbide under pressure, with a thin titanium film in between. This is the well, experimental setup, right? So we heat it up, we keep it well at a certain temperature, and depending on the thickness of the film, we either get this messy microstructure of the bond with all sorts of phases in there, or we get smooth, seamless bonding without residual stresses, and somewhere there we have well, composition results. What happens with a smooth bond? This PDF viewer is driving me crazy. Okay, it's gone. Huh? It is? Yeah. So, close the program, go away, and let's restart it. Okay, so if these are well experimental results, line scans using SEM image, and these are compositions. You see fairly uniform composition for seamless joint of all components. So it really is a seamless joint with no residual stresses. But only if the film is thin. The question is why? So here we have formulated a phase field model which shows that the driving force for this diffusion bonding is dependence of interface energy on, why is this note scrolling? Yes. So if this is interface, is dependence of interface energy on concentration jump, on carbon concentration jump. So the key question is, will you lower the energy of the system if you transfer a little piece of carbon from here, from zirconium carbide, few atoms, into titanium? And then will it keep going, and will it stop, well, at some point? So there is a rather somewhat complicated sequence of events, but I would urge you to go through this paper and to look at the model. Interesting thing about the model is here. You see, it will be one-dimensional model. We will have free energy depending on phase, and I have two phases. One phase is actually, let's look phase diagrams first. That's, well, phase diagrams of titanium carbon and zirconium carbon combinations look very similar. So we have beta phase, which is, if I'm not mistaken, BCC, and we have gamma phase, which is, if I remember well, that's B1 structure. That is like two FCC lattice of, let's say, FCC zirconium and then carbon FCC interpenetrating. Or you can treat it as one lattice, well, B1 structure, or two interpenetrating lattices of FCC type. So that's gamma phase, and we're really not going anywhere beyond this. Once you get carbon going, you get that phase transformation beta to gamma. So our phase variable here, where is the energy? I'm trying to find energy expression for phase field. Okay, so my energy will depend on phase and on carbon concentration. Then I have elastic energy, because they start bonding very quickly, and thermal expansion and carbon concentration produce eigenstrains. So if the surfaces are bonded, they affect each other, so we will have elasticity, and we have well, constant far field pressure. So elasticity depends on elastic strain, here represented by displacement gradient, phase, and carbon concentration. And then we have this term of gradients, which looks like this, right? This is a standard phase field, this first part, with gradient of phi. But the second part tells us that interface energy depends on the concentration jump on the interface, because concentration jump translates into concentration gradient when you switch from sharp interface to diffuse interface, right? Jump becomes gradient. We write our Gibbs interface energy as a constant part and a part which depends on concentration jump. So C plus and C minus, that's a positive. We decide one side of the interface is positive, the other one is negative. And then it's much easier to derive those governing equations in 1D. But in the end, our model will predict what we see, well, in experiments. This is a half of the system, so mid titanium film. We start measuring, and dashed line is initial position of the phase. So we start with, this is 5 microns, so this is 10 micron film, right? To the right we have zirconium carbide. Dashed green line is the carbon concentration, which is 0.7 in zirconium carbide, and 0 in titanium. And then, well, after a certain time, the carbon diffuses. We get phase transformation, which transforms titanium with carbon impurities into titanium carbide structure, beta to gamma phase transformation. And as carbon diffusion proceeds, the transformation front continues until it consumes the film. And then you have a binary diffusion of titanium and zirconium in time. That takes place independently. For 10 micron film, the film is completely consumed. I get seamless bonding. For 50 micron film, well, here it is. Sorry, well, I was looking at the wrong. This is a 10 micron. This B is anyway, this is 20 micron. Here's 50 micron film. So I start with well, 25 micron, that's a half thickness, right? So this is my phase here, dashed line. This is my carbon concentration, green line, dashed green line, initially. As carbon starts diffusing, my phase moves back into zirconium carbide. So the effect of taking carbon from here and putting it in, well, into titanium, well, overwhelms. The effect on zirconium is stronger, and the film actually expands, which is something that we in fact see in experiments. If I can find experimental pictures for 50 micron film, see, this is a 50 micron line, and this line here is now thicker than 50 microns, right? So for thick film, you will get the expansion. So all in all, this is one very good example of how you can formulate phase field model in 1D. For the rest of the math, I will let you well, read the paper, and I hope that this will be useful. Meanwhile, we can continue with our phase field models. The next thing we discussed last time is two types of phase field model: conserved phase and non-conserved phase. For conserved phase, we had to deal with a phase flux. And when you say that phase, the quantity of phase can be only brought by flux, you cannot create the phase, nor destroy it, then your rate of change of phase will be proportional to the divergence of the flux. And that flux will be proportional to the gradient of phase field potential. For non-conserved phase field, you can make your rate of change directly proportional to the phase field potential. So in this case, you get a second order diffusion type PDE. In this case, you get fourth order diffusion type PDE. So let's look at one specific problem, and this is fluid mechanics problem. We will then later on we will deal with a problem which deals with both fluids and solids, that is melting and flow, solid melting and flow, and then we will deal with purely solids problem with sintering and creep. But let's start with fluids because it is one simple conserved phase field. So this is a example of brazing, right? Well, we are testing brazing liquid, right? We start with brazing alloy here. This is aluminum silicon brazing alloy with few other things added. And this is aluminum alloy, and on the bottom we have alumina, that is aluminum oxide. When this is melted, it will tend not to wet the bottom substrate, but it will want to wet the wall. So as we start heating it and melting it, here's what happens, and I will accelerate this movie a little because it takes a really long time, not that much. Okay, so this cylindrical object collects into a sphere as it melts, right? Because liquid tends to take spherical shape because of surface tension. And then at some point it touches the wall, and there we go. It climbs up. This is a part of the NASA project for brazing of aluminum alloys in space. not these experiments, but we also had some experiments done on the International Space Station to eliminate effects of gravity. So, if you measure contact angle with the non-wetting surface, with the horizontal surface, and not this experiment. There were other experiments this experiment is in a surface which is too big. You cannot take it in the space, right? But we did different experiments, more compact experiments in space, in ampule, well, small ampule this size, which astronauts can take, and they can just put them there and heat it up, and then they bring them back. So this cannot be done by an astronaut. This has to be done in a lab, right? Okay, so these are the stages, and we measure position of this triple line. And we look so how it moves. So as it melts, this line moves back, but we have two types of motion. There is a sudden jump over the triple line, and there is a gradual. Well, things become even more complicated when you look at the contact angle. We know that equilibrium contact angle is 140 degrees with alumina substrate. But what we see here, contact angle goes, although it is a receding contact line. The most experiments with the receding contact line give us that contact line approaches the equilibrium contact line from below. When it's advancing contact line, you are pushing your surface, so you approach from above. But here you have dynamics which forces the contact angle above the equilibrium contact angle. And also we have two kinds of transitions: gradual transition and sudden transition from some value below equilibrium to some value above equilibrium. So this was the puzzle, and we want to figure out.
Just to be back to the slide.
Yeah.
So which one is the contact angle here? In the image.
Here.
No, I mean.
Oh, contact angle here. So if you look at in previous slide.
But it's not decreasing, no?
Right. This is your contact angle.
Right. I get that, but if you look at the let's look at the red symbol.
Well,
It's decreasing, right? That's what it is showing that it's decreasing.
where? Here.
Yeah.
Yeah, but it has a jump here.
I
Right?
understand that, but let's say if you look at figure D and E, contact angle has increased.
D and E. D and E. No, contact angle has decreased. This is contact angle. Right? This one is smaller than this one, right? So that is this path here, right? So that's a convention. We measure contact angle from the inside of the liquid, right? So that for poorly wetting liquids, we say it has high contact angle, right? That's the convention for measuring, right? Okay. Okay.
Triple line,
I'm sorry.
which one is triple line?
That's this one. That's this point here.
The point
Yeah.
contact.
Huh?
the one between alumina and the water.
Yes, yes. So we measure position of this triple line here. This one that is circled.
That is, why it is triple used? It's only two phase are there.
No, three. Liquid, gas, and solid.
Oh,
Yeah. Okay. So, what do we know about the dynamics of wetting? Well, first, this problem. If you try to solve this problem with a sharp interface model, you will run into a very significant problem. Our typical boundary conditions between solid and liquid are no slip. And we know that that is true for most simple liquids. It's not true for polymeric liquids, but for molten aluminum silicon, it has to be true. And yet, if you do that and you try to move this triple line, classical solution in fluid mechanics tells you that you will get singularity in stresses in this point. So for sharp interface problem, people try to get around it by introducing slip distance between the liquid and the solid. That, well, it can be done, but the question is, what do you base the length of that slip distance? How does it slip? Is it viscous or is it like friction? So lots of ambiguity there. On the other hand, atomistic studies have shown that triple line moves diffusively, and I will explain in some detail what that means. That means that roughly, think of motion of atoms on the surface. My fingertips are atoms, right? And if they move together, that's slip. But if they move one and then the other and then the other and then the other, even if they come into the same position in the end, but they move at different times, that's diffusion. That's diffusive motion, right? Each one jumps energy boundary and moves a little bit, and the others follow one by one. So that's what atomistic studies of the motion of the triple line indicate. So, and that is very good for our idea of phase field model, because this kind of diffusive motion is very naturally, almost automatically included in the phase field model. So let's formulate our phase field model. I have a sharp interface formulation, and if I want to write free energy, liquid, gas, I will integrate over the volume of liquid, integrate over the volume of gas. These are free energy densities. And then over liquid-gas interface to get liquid-gas interface energy. I could, and I should also integrate over solid surface, S shown here. S is a solid surface, this one, right? To get the energy, interface energy between the solid and liquid, and solid and gas. Now, this integral will have step function in it, right? So up to this point, where is my, here it is. Up to this point, it would be the interface energy liquid-solid, and beyond that, it would be liquid-gas. But step function is integrable. That's not a problem. Okay. I want now to erase this mathematical surface, and I want to make it diffuse transition. I want to formulate phase field, which will be 1 in the liquid phase, 0 in the gas phase. And if I write F of phi, this is free energy. And it has value 0 at value 0 at 1, because we are not talking about any chemistry, right? And we are doing it all at fixed temperature. So, and my phases are conserved. So I have only so much liquid, so much gas. So I might as well set those energies to 0. Right? They are constant. Those integrals are constant. I don't care about them. And then in between, I have this energy barrier, delta F. So this takes care of those two integrals. This integral is taken care of by my square of the gradient term as before, right? And I'm left with this integral over the solid surface, where my gamma now depends on phi, and so I could maybe write my gamma of phi as gamma liquid solid for phi equals 1, so it will be by phi plus gamma gas solid 1 minus phi. Right?
So why did you not take the volumetric Fidelity energy of solid in this application?
Because nothing happens to solid, right? Solid is just there. There's no diffusion in solid, there's no chemistry, we just have fluid flow, right? So why would I model something that doesn't change? If I put energy of a solid there, it will be constant throughout the process. So I'll call that constant 0, right? What you want to input in your energy are components that will change, that determine dynamics. Everything else you simplify as much as you can. Okay, so these are the basics of my phase field model for flow of immiscible fluids. So this gas and this liquid are immiscible. Gas is, in our experiments, gas was nitrogen, and liquid was that aluminum silicon alloy, brazing alloy. So they do not mix. These are conserved phase fields, but I follow the standard phase field formulation. And now I will spend more time deriving equations for solids, but for fluids I will skip the derivation phase, and I will just take you to the governing equations of this problem, which will consist, and I should really have my timer. Well, can you get me my phone? Ah, there's a clock right there. Okay, 10 to 12. Okay, thanks. Okay, first equation is almost, but not quite, what is the well-known Navier-Stokes equations for flow of incompressible fluids. So we have inertia term. Now keep in mind, this is material derivative. This d over dt. We have gravity term. We have viscous stresses. And we have pressure. Now, this animal is new. This is a capillary This is capillary stress tensor. This is dyadic. So the components of this are minus kappa phi comma I phi comma j on the basis EI EJ. So this is a tensor. This is a stress tensor. So this is capillary stress tensor, and and we will see the meaning of that tensor soon. Corresponding to that is the fact that our pi here is not a full pressure, it is a non-capillary pressure, because this capillary stress tensor will have a trace, right? There is a pressure component associated with that, so with, well, capillary stresses. So my total pressure is non-capillary pressure plus capillary pressure. Well, keep in mind, this exists only in the thin interface, right? So if this is my interface, it only exists here, outside of interface in my phases 0 and 1. When phi is 0 and 1, gradient is 0, right? Phase field is constant in pure phases. My physical parameters, viscosity, mass density, and let's leave this aside for a moment, but I will interpolate this in terms of phi, as I've shown before, so that it takes one value in one phase, another value, and changes gradually. And that way, my two phases are described by same flow equations. My two fluids flow following the same equations, even though their viscosities and mass densities are vastly different. Together with this is conservation of linear momentum equation, there goes incompressibility equation. My liquid is certainly nearly incompressible. Gas is compressible, but I will not be building up any pressures here in the gas. So gas is compressible, but we don't care. So we call everything incompressible. Now comes the, well, interesting part. My phase field evolution will be governed by fourth order diffusion equation, and you will see that it's fourth order if you substitute this m here, right? Have 1, 2, plus 2, 4 gradients, right? For the purposes of numerical computations, we typically write fourth order equations as 2 second order equations. We add one more unknown variable, so I will think of this m as my variable, right? And I'll treat this as a separate second order equation, because that is what gives you most elegant and most efficient finite element formulation. So, well, I don't have to mathematically, but I can write fourth order equation for one function as 2 second order equations by adding one more unknown function. That clear? Okay, now here comes actually, before talking about boundary condition, which I will address well on the next page, my function f of phi will be double well potential, and I will have this relationship between my phase field parameters kappa and delta f, and my physical parameter, this is liquid gas interface energy, and my computational parameter, which is computational interface thickness. two more mobilities. I have mobility in the bulk and mobility in the surface. This mobility on the surface is a real physical parameter. Bulk mobility is a fake parameter. I just need it to be large enough not to obstruct the motion of the surface. Because keep in mind, this df over dt is non-zero only within a thin interface region. Everywhere else, my phase field is constant. Rate of change is zero. So this mobility serves merely to give me computational mechanism for moving the interface is taken by fluid convection, and this simply puts interface in proper shape. So, but back to the surface. Well, I have a boundary condition which will follow from these equations, and this boundary condition will be equivalent to the mobility condition, which says this. If I have a let's say liquid, gas, and solid, and if my equilibrium contact angle is, let's call it theta naught, and if so at theta naught those three surface tensions are in equilibrium. So let's suppose my current angle is theta, then I have off equilibrium surface tension force. So this condition is mathematically equivalent to the requirement that the velocity of the triple line is proportional to the net force, net surface tension force, the part that is not equilibrated. Okay, how do we say, and if you remember Young's condition for equilibrium of surface tension, there is a cosine alpha. Well, this n dot gradient phi will have cosine in it, and this will have the difference between this interface energy here and interface energy here. But instead of sorry, this is phi, my mistake. Okay, I'll have to correct that. So instead of difference in energies, I have a gradient. Now, what is diffusive motion? Of a triple line. Imagine that these are atoms. Actually, time is for the break. Let's first see, if there are some questions here.
Gamma is the interface energy of the triple line.
This gamma?
Yes.
That is interface energy between liquid and gas.
Liquid and the gas. Okay.
Well, this capital gamma, this one.
Yes, yes. And
this one is between solid and something, because it depends on phi, right?
Okay.
For phi equals 0, it's solid gas. For phi equals 1, it's solid liquid.
Okay. But there are two solid, one on vertical wall, another in
No. Here, yeah, we could have different interfaces, but then this this function comes as a property of our boundary, okay. Right? So that's input, right? We can have different interfaces. For the original problem, yes, we have two different.
So this boundary is applicable for both?
It is the same math, but you will have for this problem, right, where you have melting and climbing. Here you will have one function, let's call it gamma 1 of phi, and here you will have different function, gamma 2 of phi. But see, this function comes as an input, right? So you can have multiple ones, doesn't matter, right? It's there as a property of that surface.
It is okay. We have to know it from literature, means.
Yes, yes.
Okay.
Yes, well, you have to know some material properties.
Okay.
Any more questions about this part? We will test the model pretty soon, well, as we continue. Okay, then let's have a break. No questions in the chat. Okay. So we're going to have a break. 5 minutes. Yeah, just tell them we're starting. Okay. Okay. So, okay. So let's see the slides. Yeah, here it is. Okay, so what is diffusive motion? Think of atoms on the surface. These are those blue atoms. And let's think of 3 time scales. Atomic time scale, which later on today Shoumik would tell you is of order femtoseconds, picoseconds, very, very small. Let's think of some mesoscale, which is much greater, orders of magnitude greater, nanoseconds to microseconds maybe. And the continuum time scale, which is much longer. And really, these are mesoscale models, but we are resolving on a continuum time scale. Mesoscale is something that happens way too fast for us. So, well, if I look at those atoms, and if on a well, on a mesoscale, I see I look at the time t and t plus delta t. And this delta t, that's of the order of t mesoscale. If on the mesoscale I see those atoms that they have all moved by pretty much the same amount, then I say my fluid is slipping over the surface. If on the mesoscale I see one atom moves, and then after some time interval the other one moves, and after some interval the third one moves, and they all move by the same amount. The final result is same as here, but on the mesoscale they don't move synchronously. Then we call that diffusive motion. So for slip, I will have the difference in the tangential velocity of fluid and solid. For diffusive motion, I will have a rate of change of the phase field on the surface. So if I were to write the equilibrium of liquid, gas, solid, that is equilibrium of surface forces, right, surface tensions. And if I were to write a phase field equivalent of that, it would look like this, right? This n dot gradient phi, that has sines and cosines, right? When you project those, you all remember Young's equation, right? Just the projection of forces. Is this force by cosine of the angle must sum up with those two horizontal forces to 0. That projection that's here, that's trigonometry, this gives you the difference, right, in this surface tension and this surface tension. So the equilibrium of the phase field triple line. So for phase field, triple line is not a line, it's a triple stripe, right? This is where my phase field variable changes from 1 to 0, and this is where my interface energy or surface tension changes from solid liquid to solid gas, but it changes gradually, right? So this is my triple line. It's a triple stripe normal to the surface. This is the equivalent of Young's equation for phase field. But I want a moving triple line, so that triple line is not in equilibrium. So I will have rate of change of phi proportional to the discrepancy from equilibrium, right? The value of this should be 0 in equilibrium. Any difference from 0 gives me the imbalance in those surface tensions. The simplest model is linear, so I have surface mobility, right? I still keep no slip boundary condition, so the fluid is still not slipping, so I don't have to deal. Okay, so I still have the difference between fluid velocity and solid velocity. Well, for tangential velocity gives me no slip, and for normal velocity tells me no penetration. Again, this is very important because if I cannot for traditional fluid dynamics with simple fluids, if you put no slip boundary condition into sharp interface model, you're getting singular solutions. You cannot solve for it. Why? Well, that's clear. If there is no slipping here, how can this line move? Well, how can this point move if you don't allow slip? But in diffuse interface model, you have diffusive motion, which is different from slip. You still have no slip, but a diffusive motion of the triple line. Okay, so let's test our model, and let's first try equilibrium. This is useful because here you will see the meaning of those of the surface stress tensor, at least volumetric part of it. So 2 vertical wetting walls, two-dimensional problem. Some liquid down here, some gas up here, right? Well, solid walls and a horizontal substrate all have the same. All walls have the same properties, and we are just using phase field model to find the equilibrium. The good thing here is that we have analytic solution for equilibrium. So at least we can test our phase field model on an analytic solution, and it works perfectly. Well, as you can see here, this thin white line, that's our interface thickness. That's where we change from red to blue. Okay, but let's now look at pressure in the y direction. So we're looking at the pressure along this line. This is my y axis, right? So, well, I have gravity. So since I have a heavy liquid here, my pressure is decreasing from the maximum value at the bottom. Actually, let's first think of sharp interface model. That's this solid line. My sharp interface model will tell me linear pressure increase up to here, then jump, right? Here I have a curvature, and I would have jump in pressure, right? If you have P1 here, and then you have surface tension, right, gamma, and P2 here, this surface tension will cause a jump, right? That clear? So my sharp interface model gives me a jump in pressure here, and then in gas, low density, nearly constant. Well, you can put some small density, and I think you have some small density, but this is These are small dimensions, so you practically see no change, right, in pressure in gas. What happens with the phase field model? Pressure in liquid goes well until we get to the interface. Then the surface tension, the surface stress tensor, this term, picks up. And that stress tensor has a trace. It has a pressure corresponding, pressure component. And then that pressure component will be negative pressure, right? So we go deep, deep, deep into negative pressure. That is, in fact, surface tension. Right, that's what, and note that this graph is interrupted here because this is minus 220, right? So the integral of this will give you surface tension. And then at the end of this thin interface region, we come back up to what should be in gas. So given the assumptions, our phase field model seems to be working perfectly, at least for equilibrium. Right? So let's see what happens with our contact angle overshoot that we discussed, right? In our no standard model can explain the this contact angle going up above the equilibrium contact angle of 140. Sorry, these are simulations for 100 and yes, these are simulations for 140. So the contact angle, the blue are experimental results, the red are computational results. Notice that in the end of this problem, we will not have a perfect contact angle because we have a this contact angle here comes between it is in the corner, right? So if it was on the flat, it would be 140. But because it is in the corner, it is indeterminate. It depends, right? You cannot write Young's equation in the corner. So we need something. This requires explanation. What is happening with this contact angle? Yes.
That experiment was happening at what length scale?
Let me see. This is. I think I had it somewhere here. There were some dimensions. Okay, these are dimensions. 20 millimeters, 15 millimeter height, 10 millimeter depth, right?
You took the video with the help of a camera?
Yes, there was a high-speed camera inside the. It's all happening inside the chamber, which is heated to somewhere around 610 Celsius, 610, 620, 30. That's enough to melt you technically, and then we just this is what you see. Okay.
And this is example of conservative phase field, right?
Yes, yes, that's a conserved phase field. Okay, but then let's try some shorter time scale. Let's try a little ball, little sphere. So if you take this same alloy and shape it into a sphere, well, it was not sphere initially, it was cube. But if you melt it fast, it makes a sphere, but it makes contact angle here, which is roughly 170. And then after approximately 10 seconds, this contact angle deteriorates to 140. So what we call, so this is equilibrium, but this involves some chemistry. There is aging of the contact angle. What happens is that this compound has well, some components which are designed to break oxide on the surface, well, of the aluminum. Once that breaks, we get this, well, this contact angle. Before that, for a short period of time, we get higher contact angle. So pure compound without any oxide on the surface will not wet at all, will barely wet, 170 degrees. You get slight wetting when you break down the oxide. So we introduce a state variable. We will call this, well, equilibrium contact angle, but now we treat it as a state variable which varies with time. From it starts from value alpha naught, which is this big angle, and exponentially decreases to value alpha 1, which is final equilibrium contact angle. So if you introduce that, here's what you get. We are able to explain qualitatively everything that we have seen, well, in experiments. Well, among other things, there is a gradual change in contact angle or very rapid, abrupt change in contact angle. Overshoot in contact angle over the equilibrium contact angle is there. But most importantly, we discovered what is the reason for sometimes gradual and sometimes abrupt change in that receding contact angle. And you can see that in, well, in these movies. If you look at this one, and let's you see this is the bottom contact, right? And then if I move slightly that bottom contact will connect with this contact. This is a contact with a vertical surface. This is looking from the bottom, right? So you see how those two surfaces connect and become one surface. In this case, that doesn't happen. This contact just disappears, and this one then spreads outside. If you look at it in profile, you see how this contact angle moves. But if you look at this case in profile, contact angle jumps. So if we go back, a little bit more back, so see here you have this contact here, separate contact. And you have a gas here. But instead of this contact connecting with this contact will break. And when it breaks, you cease measuring this contact angle and you jump to this contact angle here. So we have concluded that this jump in contact angle that we see here, where are those plots? The jump in the contact angle that we see here, and this rapid separation and gradual separation. Well, rapid separation is the second case, where you have a breaking of the contact. And that is something that you really cannot see, well, in experiments, right? Because that's the part that is hidden from you. You cannot see, well, this is looking from the bottom, and you don't see the bottom. You don't see that this contact disappeared. This one. And that in the other case, this contact simply, well, connected with the other contact. So this is the results of the phase field model simulations that I just shown you. And we were not able to get quantitatively, well, all the results, because there is a problem when the liquid starts flowing. It's a mix of liquid and solid particles that are yet unmelted. So that's the next step. We are going to the more complex model to explain that. But qualitatively, we have explained the behavior of the triple line.
So which one of these is more close to reality?
Sorry?
Which one of these four is more close to reality?
We see both cases in experiments, right? This depends. This depends on the. Sorry, what are you? We have different experiments here. You see, there is a very large error bar in experiments. There is a randomness in experiments which depends on surface roughness, on how quickly we heat the thing, how much oxide do we have. So both things can happen. And in the end, we concluded that it really depends on how fast the flow starts and how well melted the material is. Because when you have a high viscosity, very high viscosity, then you will get this separation. When you have thoroughly melted material, and that means low viscosity, you will get smooth transition. Because if you look at here, what happens is while this is melting, okay, now this is collecting material now, and it's turning into a sphere, right? Let's move a little bit forward, yes. Now, when will it touch? Well, if it touches too early, then your material is full of solid residue, and it's very viscous. So the effective viscosity is high, and in that case, you will get this separation. This. In the case of low viscosity, well, if it gets the time to melt all the crystallites inside, and then it touches, then you have a low viscosity fluid, and this will happen. So you will have gradual transition.
And so this yield better brazing result. Which one?
Sorry?
Which one will yield better brazing result?
Which one will yield better brazing results? I don't think it matters. Well, this is rather superficial configuration for brazing. Well, for real brazing, we have to look at a different experiment. If you have non-homogeneous melting, and if you start taking away your liquid very soon, then you will be left with unmelted material, right? So you don't want to start flow too soon. But this is not the right example to show that. I will now go to the much better example. Any more questions here? Okay, so what I want to do now is I will, this is a part of the same project. These are the samples that were sent to International Space Station, right? And they were within an ampule which was filled with nitrogen. We tried nitrogen and vacuum, but well, vacuum was not very good, so those experiment fails, but we still have nitrogen experiments. So, well, here's what happens. We start with this initial configuration. This is aluminum alloy cylinder. This is brazing alloy here. This is brazing alloy on the top. And this is all placed in alumina frame. I think the correct word is, well, crucible, right? So, alumina crucible. This is a vertical section. There is a tube of aluminum, and there is a brazing alloy here. So when we well, when you start melting, as this melts, on Earth you have gravity, but in space you only have capillary forces, which will pull this. This brazing alloy does not want to be in contact with alumina, doesn't wet alumina, but it does wet aluminum or aluminium. So how do you say in India, aluminium or aluminum? Aluminium. Yeah. So it's only Americans who say aluminum. Okay. So well, aluminium and well, alumina, that's aluminium oxide. Okay, so this melts, and this is a short time. This is longer time results. Melts, and then you cool it off, and it's solidified. So what happens? Why am I getting this standard dendritic solidification here, while here I'm getting something that looks spherical pores and tiny white spherical grains or something? Why am I getting such a different microstructure? So, well, here's what happens. This is a phase diagram of aluminium silicon. Well, our brazing alloy is somewhere just below eutectic. So 11 or maybe 12%. So just below eutectic. So what happens is that when you start melting your alloy, you have your alloy, of course, is in equilibrium, or at least close to equilibrium. So what you have is you have grains of FCC aluminum. So this is this phase, and you have lamellas, or maybe a near spherical particles on triple junctions like here, or grain boundaries, right? Much less silicon, of course. That's this phase here, right? You have mix of silicon and aluminum phase, and then you start heating, right? At this nominal concentration. Well, the lowest composition that will melt is the eutectic one, right? So as silicon diffuses, the first area to melt is the one near the interface, right? Now, if this melt percolates, so well, sooner or later, well, it will percolate, and then you get a flow, right? If you have well, isolated ball of liquid, well, inside the solid you don't have a flow, but when it percolates, it starts to flow, and what you have is basically very wet granular material at that instant. Well, granular being pure grains, nearly pure aluminium grains, and aluminium silicon liquid in between. So what happens here is that the liquid is pulled out and away towards the bottom, and what remains on the top is some sort of granular material which looks something like this. These are aluminum grains, and the gas comes from that additional compound. Chemical reaction with the oxide, well, produces a gas, or it could be nitrogen. Aluminum grains and gas inside, and then if you pull this liquid quicker than you can melt, you have taken out, well, all the silicon, and you will not melt many of the grains. So you're left with small, if I can magnify this, well, if you were to magnify, you will see the white little grains like here. Black things are the voids, right? That's the gas, and they're because of surface tension, they have this is melt around the grains that has solidified. So what you are seeing here is grains of aluminum, right, white, and then the liquid has solidified, well, in a spherical shape. This is aluminum silicon liquid. These are white grains, and black, very black holes. These are voids, right, and they're spherical. Here you see the typical eutectic solidification with dendrites. So we are solidifying from near eutectic composition, dendrites and everything that you see in traditional metallurgy. So that's qualitatively what happens. But can we simulate it? How do we represent a model? So what will be the phases in our model? I have alpha solid, alpha that's aluminum, FCC. I have silicon solid, that's diamond structure, right? Usual crystalline structure for silicon. I get liquid, which is the mix of aluminum and silicon, and I have inert gas. These are the phases in my problem, 4 of them. But then I have concentrations, right? I have 2 components, C1 aluminum, C2 silicon. My phases will have to satisfy the condition phi1 plus phi2 plus phi3 plus phi4 equals 1. So I'm either in one phase or in the other, and if I'm not in any single phase, then the sum of all the phases must add up to 1. Right. So in this case, well, previously we have dealt with a single phase field, right? And that phase, because we had only 2 phases. When we have more than 2 phases, we introduce multiple phase fields. So previously our phase field being 0 meant phase field equals 1 meant phase 1, and phase field equals 0 meant different phase. Here it means anything but 1. Right? So when phi1 is 0, that means that I am not in aluminum solid. Nothing else. I don't know where I am, that particular point. It could be any of the other phases. Same thing for phi2, phi3, and phi4. Now this is an extra condition which will have to be enforced by means of Lagrange multipliers, and I have just noted here those Lagrange multipliers. Now, pressure will not play much role here, and the change of volume is not very... I do have few % change of volume, liquid to solid, but because there are no mechanical constraints which would prevent shrinkage and growth, it's a flow. There's lots of fluid. Well, I don't care about the change of volume. So I don't care about elasticity, well, in this problem, which makes the problem much simpler, right? Because we don't have to deal with stress tensors and all that, and strains. So I will treat all phases as incompressible. And finally, I have different concentrations in aluminum phase and in liquid phase. But okay, what is liquid phase here? Phi1 plus Phi2, Phi3. And in silicon, but Phi4 is inert gas, so I don't have any concentrations in the 4th phase. So I have to make sure that my where I have concentrations, they add up to 1, right? I have only 2 components, aluminum and silicon, so the concentration C1 plus C2 will add up to 1 in phases 1, 2, and 3, but will be 0 in phase 4. So in gas, when phi4 equals 1, those 3 guys are 0, right? So, well, I don't have any aluminum or silicon. And okay, now next time I plan to get with some details into the governing equations, but I think I would end up this lecture here now, and then we will talk more about this problem next time, because this is a big chunk to swallow, the next piece of material. Any questions? So we've stopped here. Any questions so far?
The aluminum is also getting into liquid state. Aluminum is also getting melted.
It's melting with silicon, because we never raise temperature. Temperatures in the experiment go up to 610, 620.
Okay.
Actually, never above 615. 610 is nominal. So which means that this pure aluminum will never reach melting temperature, right?
Okay.
Only it needs some silicon to melt.
So only in the interface the liquid
Yes, yes, it melts from the interface as the silicon diffuses. And if you kept all the liquid confined, the silicon would diffuse, and in the end everything will melt. Everything would melt. But if you take away silicon rich liquid, then there's no silicon to help aluminium melt. And these grains here, these are the grains that have never melted.
The grains.
Those little white dots. Maybe I can magnify this. Let's try it. If I okay, view. Yes, I think you can see them now.
Okay.
See the white dots. Here. This is too thick a line. Something sharper. Where is a nice white dot? There's one here.
So that means
Oh no, this is not good. This is not very. Maybe I can. Okay, let's do the smallest line. So this is unmelted grain here, and this one, and this is a series of unmelted grains here. You see. And in between those, and here, see here, 1, 2, 3, and in between this is near eutectic liquid which has solidified, and this avoids gas.
so what we have achieved with this means it is not a brazing.
Sorry?
This is not a brazing. Means we have
No, we are doing experiments with brazing liquid to see how will it behave in different conditions without gravity. How will it flow?
Okay.
It turns out that surface tension is enough to make it flow.
Okay.
So brazing in space without gravity has two problems. One is that you are the slave of surface tensions. Right. If you were to, well, you know how when you put a straw in your drink, and then it makes a meniscus, the level in the straw rises a little bit higher. Well, if you did the same in space, it would rise all the way, and liquid would cover everything. Because on Earth, well, surface tension fights gravity and fights some equilibrium, which is slightly higher than your level. But in space, well, the liquid would want to cover
Liquid will come out completely.
everything. Yes.
Okay.
So, so that's the problem if you want to do brazing in space, right? You need to melt something, and where will the liquid go? You want it to stay somewhere, right? To form a bond. Another problem with brazing in space is brazing has a chemical reaction when you break oxide, well, on the surface. That chemical reaction produces gases. Now, well, here are those gases here, right? You see them. But if you are maybe I could use this for drawing. If you are on Earth, right? Gas nucleates, well, on the surface, creates a bubble, and then because that bubble is held by surface tension, right? Until it becomes large enough that buoyancy forces push it up, right? But buoyancy forces exist in gravity. They don't exist without gravity. So if this bubble, well, it can be calculated that on space station, on International Space Station, your bubble has to be 1,000 times larger to separate from the surface. So they will not bubble up on the surface of the liquid. And so, well, if you do brazing and those voids remain in your brazing joint, that weakens your joint. So these are two problems with brazing in space. Surprisingly, gravity plays an important effect. Okay, any more questions? That's it for today. Lunchtime.